Hello everyone. In this lecture, we'll learn about enzyme kinetics. So, what is enzyme kinetics and why it's necessary to understand enzyme kinetics. So, biochemists they commonly use several approaches to study the mechanism of action of purified enzymes. Okay, the three-dimensional structure of the protein provides important information, which is enhanced by classical protein chemistry and modern methods of site-directed mutagenesis. Site-directed mutagenesis means we can change amino acid sequence to a particular or specific places by changing the DNA. That means using genetic engineering, we can change the amino acid sequences. So these approaches or technologies permit gymologists to examine the role of individual acids in enzyme structure and action. That means the gymologists who study the enzyme, by using this approach, they can study the mechanism of enzyme. Okay, and also they can study which part of the enzyme have which play which role, which part of the enzyme is enzymes are made of amino acids. So we can say in other words that which amino acid or which amino acid sequence do what kind of role in that enzyme. Okay, so however these are not the all. Okay, the oldest approach to understanding enzyme mechanism and the one which is still remains most important is to determine the rate of a reaction and how it changes in response to changes in experimental parameters. Experimental parameters means pH, temperature, etc. And this discipline of study is known as enzyme kinetics. Okay, so kinetics is the study of the rates at which chemical reactions occur. Okay, so while thermodynamics only determines whether a process will happen spontaneously or not, kinetics describes the way a reaction proceeds and how that journey is affected by the surrounding. So, a study of kinetics means deal with the rates of the reaction, right? So, let's see what we understand about reaction rates. So the rate of any reaction is determined by the concentration of the reactant or reactants and by rate constant. And this rate constant is denoted by K. Such as, suppose this is a unidirectional, this is a unimolecular reaction. I mean from S to P. S is the substrate, P is the product. We can uh, we can show the rate or velocity of the reaction by this equation. V is equal to K into S. Here S is to represent the concentration of the substrate and K is a rate constant. Okay, so for this reaction the rate depends only on the concentration of this substrate. Okay, this is the only variable here, so that's why this is called a first order reaction. Okay, and the factor of the constant K is a proportionality constant that reflects the probability of a reaction under a given set of conditions. What conditions? Like pH, temperature, etc. Okay, so as this is a first order reaction, this K is a first order rate constant and it has units of reciprocal time such as per second. Okay, s to the power minus 1. I mean this is the uh, unit of the constant. Okay, okay, so a reaction with a so what we understand by these things. Okay, so a reaction with a rate constant of 2000 per second, what we understand by this. So this means this reaction will occur very fast, I mean 2000 per second. Okay, so that means this reaction will be over in a very small fraction of a second. Okay, 2000, I mean if you fraction a second into 2000 small pieces, so this reaction will occur within in one piece. Okay, so very fast, like 2000 times. Okay, I mean per second 2000 reaction will occur. I mean in other way we can also say this. I mean this reaction will for this reaction in each second 2000 reaction can occur. Okay, so If a reaction rates, okay, now we talked about the first order reaction. So this is not the only one type. There are other types. You actually already know that. Yet, for recap, if a reaction rate depends on the concentrations of two different compounds, or if the reaction is between two molecules of the same compound, then the reaction is a second order reaction. Okay, and in this case the K is a second order rate constant, and which has a unit of per molar per second. Okay, so you can see the units of the K is different. I mean, it depends on the order of the reaction. While first order the unit was per second, for the second order the unit is per molar per m per second. Okay, so I mean, if you imagine this reaction, the rate of the reaction will become like this: V equal to K into S1 into S2. Here S1 and S2 represent the concentration of the both substrates. Okay, this S1 is the concentration of the first substrate, and S2 is the concentration of the second substrate. Okay, so we already know about the transition state theory. So from transition state theory, we can derive an expression, reaction expression that relates the magnitude of a rate constant to the activation energy. That means with this equation, we can relate the rate constant with the activation energy. Okay, we can establish a relation between the rate constant and the activation energy. And the equation looks like this. Okay, K equal to K T divided H e to the power delta G by RT. Okay, so here K is the, okay, new K came here. So this 2K, I mean, are not the same. Okay, one is rest constant, another is a different constant, and this K is the Boltzmann constant, and H is a Planck's constant. Okay, so the relationship between the rate constant K and the activation energy is inverse and exponential. Okay, because activation energy is here. Okay, so that's mean the relation is between the activation energy and the constant is inverse and exponential. Okay, and so that a lower activation means a faster reaction, a higher activation means lower reaction, so that means inverse type reaction. Okay, in a biomolecular reaction, okay, so if one substrate such as A is in much lower concentration than the other substrate B, then the reaction rate will depend on concentration of A and will appear first order in respect to A. That's why this is called a pseudo first order reactions. I mean, this is not a monosubstrate reactions, so this is a you can say the bisubstrate reaction. I mean, there are two substrate, but as the concentration of one substrate is very low, so that the reaction of this rate of this reaction will completely, the rate of this reaction will completely depend on the concentration of one substrate. Okay, so that's why it is called as, and the reaction will act like a first order reaction. So that's why it's called a pseudo first order reaction. I mean, it's not a real first order reaction. There are two different substrates there, but as the reaction rate depends on the concentration of only one substrate, that's why it is called a pseudo first order reactions. Okay, and in case of zero order reactions, the rate doesn't depend on any of the substrate concentration. Okay, okay, now we understand the reaction rates and okay, however, so there are several factors, okay, which affect the reaction rate. That means these factors control the reaction rate. Okay, I mean, these factors can make the reaction faster or slower. Okay, so what are these factors? These are those factors, okay, which can influence the rate of a reaction, such as substrate concentration, product concentration, different inhibitors, temperature, pH, etc. Okay, so we will not discuss about all, I mean, how all these factors affect the reaction rate, but at least in this lecture we'll talk about the effect of substrate concentration on reaction rate. Okay, so what we understand by the what kind of effect a substrate concentration can exert on reaction rate. Okay? So the substrate concentration, which is denoted by this way S enclosed with third bracket. Okay, the substrate concentration changes during the reaction. Okay, so it is difficult to monitor its effect because when the reaction is go on, the substrate will react. So that's why its concentration will be in constant change. So for this reason, it's actually difficult to monitor its effect. So how we can do that? Okay, it is difficult. Okay, we understand that is why it is difficult to monitor, but still we need to monitor, right? We need to understand how I mean the change of substrate concentration or the substrate concentration is affecting or influencing the reaction rate. So one simplifying approach in kinetics experiments is to measure the initial rate, which is designated by V0. Okay, V0 means it represents the initial rate. Okay, so however, anyway, in a reaction, an enzyme may be present in nanomolar quantities. That means very low amount, whereas substrate may be 5 to 6 times higher. Okay, higher than the concentration of the enzyme. So now, what happens in the beginning? In the beginning of the reaction is monitored. Okay, like say first 60 seconds, when change in substrate concentration is not much and can be regarded as constant. I mean, we know that the concentration of the substrate change, but for the beginning, usually like the first 60 seconds, we can say that I mean the change in substrate concentration is very low, very negligible. That's why we can consider that in the beginning the substrate concentration is constant. Okay, so the initial rate of velocity v0 can then be monitored as a function of the substrate concentration. Okay, so now, at relatively low concentrations of substrate, V0 increases almost linearly with an increase in substrate. I mean, if substrate concentration is low, so if substrate concentration increase, the velocity, initial velocity of the reaction will increase. Okay, a linear relationship. But in contrary, if the substrate concentration is high, V0 increases by smaller and smaller amounts in response to increase in substrate concentration. Okay, so if substrate concentration is high, although we add more substrate, that means we increase the concentration of the substrate, the increase of reaction rate will not be linear. Okay, instead the reaction rate, yeah, that means the initial reaction rate or velocity v0 will increase by smaller and smaller amounts. Okay, and finally a point is reached beyond which increase in v0 are vanishingly small as substrate increases. I mean, this is about the when about this scenario when substrate concentration is high. I mean, although we'll add the substrate concentration, the increase of V0 will be smaller. Okay, and actually it will decrease. I mean, the rate of increase will eventually decrease, and finally it will reach to a point where although we increase the substrate concentration, the increase of V0 will be very small, almost into a negligible point. Okay, and this plateau like V0 region is close to the maximum velocity Vmax. Okay, that means we are adding substrate, but the rate will not increase anymore. So this will represent the maximum velocity, which is denoted by Vmax. Okay, so this thing, I mean, what I talked here, we can represent it in a graph. Okay, so this graph represent the relationship between substrate concentration and initial velocity. Okay, say in x-axis if you put substrate concentration and y-axis initial velocity, that is v0, the change in initial velocity will look like this. Okay, initially the change of the velocity will be high. Okay, that's why the graph will look like this. Okay, but eventually the increase will decrease. I mean the rate of reaction rate increase will be slower, and eventually they will come to this point where the change in reaction velocity is so smaller that almost it becomes a it stays at a constant level. Okay, so this point is called the maximum velocity. Okay, the velocity at this point of this reaction is called Vmax, maximum velocity. Okay, so that's all for this part of this lecture. In the next part, we'll talk about ES complex, because ES complex is very important. It is the key to understand the kinetic behavior of a reaction. Okay, so till then, be safe. Thank you.